Okay. I'd like to present you our scientific research on the topic of intelligent monitoring system for analyzing vehicle driver state based on adaptive deep learning models. Problem statement. The advancement of modern technologies and the increasing computational power make intelligent big data analysis systems essential tools for automating complex processes and making well-founded decisions. Road traffic safety is becoming an increasingly pressing issue, necessitating the implementation of innovative methodologies and technological solutions aimed at minimizing the likelihood of traffic accidents and enhancing driver protection. A critical aspect of this issue is the physiological and psychological state of the driver, including their level of concentration, degree of fatigue, emotional stability, and ability to respond promptly to changes in road conditions. Consequently, the study and development of highly effective driver state monitoring algorithms and systems have become priority areas in the field of transportation safety. Thus, the development of driver state assessment approaches based on video analyzing using deep learning techniques representing a promising direction in transportation safety. Intelligent monitoring systems built upon these technologies can promptly respond to changes in driver conditions, mitigation the risk of accidents. The integration into modern vehicles has the potential to significantly enhance overall road traffic safety. According to the analysis of a number of literature sources and the opinion of authors, in practice there are various methods for determining the driver's conditions, the most priority and promising of which are based on wearable sensors processing the driver's visual conditions and the acoustic environment. Current methods for assessment driver states based on sensor data and acoustic environment analysis have several limitations and reduce their effectiveness in real-world applications. Uh, Physiological sensor-based technologies, for example, heart rate monitoring or galvanic skin response, face challenges related to invasiveness, complex calibration requirements, and high sensitivity to individual psychological variations. Furthermore, these systems require continuous physical contact with the driver, which can cause discomfort and limited visibility. Acoustic analysis-based approaches also exhibit constraints such as susceptibility to high background noise levels within the vehicle cabin, variations in individual speech patterns, and the need for complex signals processing to achieve high detection accuracy. Additionally, these methods are less effective when the driver remains silent or exhibits minimal speech activity. So the goal and system structure. The aim of this paper is to develop intelligent monitoring system for analyzing vehicle drivers state based on adaptive deep learning models. Actually, it's not only monitoring but analytical system. To address the outlined problems, the following concept of intelligent monitoring system for analyzing vehicle driver state can be proposed. Development Systems First model, M1, with deep neural networks adapted for existing deep learning models for detecting key points on the face and head, with the purpose of binary and multi-class classification, aimed at assessing the driver's level of fatigue. Development Systems Second model, M2, also adapted from existing deep learning models for detecting distractions affecting the driver during driving. Aggregation of the outputs from M1 and M2 models to enhance results accuracy and reduce the number of false positives. On this slide, we can see system general scheme. As we can see, we use data set loading, which includes driver and attention detection data set and driver drowsiness data set, which are common used data sets in Kaggle platform that we can combine in our monitoring system as input data to make our first EDA model, convolution neural network customization, when we can explore data formations, train and test data frames, grid search using for finding the optimal parameters, hyperparameters for models, training and testing custom models, evaluation, and metrics visualization. Next step is using Model 1 and Model 2 to use adaptation, different neural networks from submodel adaptation. For example, models VGG16, EFNet, ResNet, and MobileNet, which are used for making such processes as fine-tuning, evaluation layers, freezing, regularization. After that, we combine all the results of our free models and submodel to comparison and weighted assessment of the driver's condition, and then model serialization for the deployment and integration in vehicle system. In this slide, we can see example of our custom convolutional neural network model structure, where we can use couple of layers and use a flatter, dense, dropout parameters, as we can see on the slide, which provides with a grid search. Total number of parameters is about 20 million, 90 million. On this slide, we can see F1 score and prediction metrics results for adaptive deep learning models in Model 1. We can see F1 score for classical custom CNN, ResNet, and MobileNet. For example, we can see that ResNet shows us the best score in all these metrics. On this slide, we can see construction error matrices for adaptive deep learning models in Model 1, where we can see predictions made by CNN is worst, ResNet is the best, and MobileNet is near the best results, but have some errors. And on this slide, we can see currency loss for custom for our free models. We used in models this accuracy in general for currency and loss with which shows us the difference between training and validation processes, and the trend, which we can see that MobileNet is have a little less results in accuracy, but more lower falling with a loss. On this slide, we can see accuracy for validation and training for improved adapted models, because we, after training our free models, additional training of our two models, MobileNet and ResNet, and first training for our custom CNN model, we discovered and combined also EfficientNet B0 and VGG16 models, and built a comparative graph with training and validation accuracy, in which we can see that MobileNet show us the highest level of values on this graph. But also we can see that about 100 epoch is the main part, the main point, which we can see that after this point, most of models shows us oversampling, overlearning. So we need to use a regularization on this point to stop models being wrong. In conclusion, we can discover and say that the research results demonstrate us the effectiveness of fine-tuning and the adaptation of existing deep learning models, especially MobileNet V2 and ResNet 50, in develop intelligent monitoring system for analyzing vehicle driver state. By leveraging pre-trained architectures, the models achieve high classification accuracy while reducing computational costs and training time. ResNet 50, with its residual learning framework, effectively captures complex feature representations but exhibits higher computational demands. In constraint, MobileNet V2, optimized for lightweight and efficient deployment, ensures fast inference while maintaining competitive accuracy, particularly in tasks focusing on region analysis. The results indicate that both models generalize well when fine-tuned on domain-specific data sets, which we showed before, particularly in detecting signs of drowsiness and distraction. As observed, the MobileNet V2 model demonstrates a more accurate assessment of the driver's condition, particularly when analyzing segments containing the ocular region. Moreover, its performance is 2-3 times faster than that of ResNet 50 model. This can be attributed to the fact that ResNet 50 considers a broader feature space and possesses a more complex architecture, leading to an increased size of serialized objects and weight values. Thank you for your attention.